All right, so last time what we did was we finished up the homonuclear experiments. So we went from the, I didn't change that though. This is supposed to be DQF, double quantum filtered cozy, the long range or relayed cozy, the TOXI, total correlation spectroscopy, and the NOSI. So the NOSI is the NOE. And then there also is, which we could write in here, there's another version of this NOSI, which is called ROSI, for rotating frame, I guess, nuclear Overhauser effect spectroscopy. So the advantage to that is, I think we talked about a little bit one time, where the NOE, the amount of NOE versus, and this is just simplified down, versus the, let's say, the molecular weight of the compound. So it's not really the molecular weight, it's like how it tumbles in space, but is generally related to the size of the molecule. This NOE, if this is 0, kind of goes something like this. Oops, I didn't mean to have that hump there, though. But it kind of goes, if they're smaller, then we get positive NOEs, like we've been seeing. We call it an NOE enhancement. So when we did the difference NOEs, if we subtract, then we got some positive signal. But if it gets above a certain molecular weight or tumbling, gets slowed down enough, then the NOEs become negative. And there's a point right here which oftentimes ends up being about like 1,000 molecular weight, where the NOE goes through 0.
What's the reason for that?
I don't really know exactly.
Empirical of the heat is behaving.
Yeah, I'm sure that there's a reason, but the ROSI experiment gets around this problem. So it's better, this one's better for, when we have the molecular weight, around 1,000 or something. So if you get up into that size, then the ROSI can be better. All right, and so we just looked at a few examples. Then we started in on the heteronuclear correlation experiments, and so we talked about or saw some examples of, we talked about the differences between C13 and proton detection, and we saw an example of a het core, which is a C13 detected experiment, and HMQC, which is a proton detected experiment, and both of these are one bond carbon hydrogen coupling experiments. So they essentially tell us which protons are attached to which carbons. So today what we're going to do is I'm just going to show you some various examples, and we're going to include in an experiment called the HSQC, which is kind of a, younger brother of the HMQC. So it is, again, one bond couplings. And then we'll add in the HMBC, which is a multiple bond correlation experiment. So usually that's kind of optimized for 2 and 3 bonds. And then we'll look at examples and things like that. And then if we get there, we'll talk about this inadequate experiment, which is a homonuclear C13 coupling. So it's kind of an ultimate experiment, but it's very insensitive. And so it's not as much of a practical application.
It's not good enough.
Yeah. All right. And then after that, we probably won't get there I didn't have any slides that I brought with me. After that, we'll work some problems and stuff next time. Okay, so this is kind of where we stopped, and so I'm just going to run through examples that are not only of just 2D, but I've got just kind of a data set for this compound. And we talked about last time about terpenes and how this is a terpene, and that helps us sometimes, put things together if we know that there has to be kind of this repeating pattern of atoms. So if we look at the proton NMR, there's probably just a few things that we could pick out just from the proton NMR. So what do you think we could identify here as far as assigning some peaks?
The 3.4 is by the alcohol.
Right. So these are these two protons here. Notice that, in fact, if you look at this peak, it's a little weird. This one looks more like a singlet. This one's split a little, and there's some stuff down here at the bottom. So I think what that is that these two protons, well, they're diastereotopic, and their chemical shifts are just very slightly different. But they're coupling strongly to each other, and so this is a very second-order diastereotopic pair of protons. And so the other things, I think this is probably the OH. And then, of course, we have two methyl groups, right, which is a little hard to know, I think, which one is which. But then, there's just a bunch of other CH2 groups and CHs. It's hard to assign those at this point. Though, the proton NMR, those methyls were really quite far apart, right? So look at this one. Well, this one's at 0.8, and that one's, I can't even see what it is. But, they're chemical...
1.2.
Okay.
Maybe.
But they're quite different, so...
Both of the methyls are like the most upfield. We generally imply that the carbons would be more, or like the most upfield, right? And so I guess that was my thought process on why the
Right, of course.
Yes.
Yeah, no, that seems reasonable.
Okay, all right. I was just double checking.
Yeah.
Okay.
No, they are in the proton NMR, right? They're quite different from one another, but they are the most upfield signals.
Yeah.
Okay, so here's the C13 NMR. Of course, there's no aromatics or anything. This is the solvent.
Which one is solvent?
The three peaks,
The middle?
all three of those.
Oh, okay.
So remember that for deuterated compounds, that the deuterium has a spin of 1, right? So what was that? 2I times 2n, or n plus. So it ends up that deuterium splits that carbon into 3 peaks. So the center peak is usually put at 77.0. So this has got to be the carbon with the oxygen on it, right? Anything else you might propose?
Say the
Just in groupings or...
yeah. I mean, like the.
Can you say the quaternary carbon based on the small peak?
It could be. This one here
Yeah, that one.
could be the quaternary carbon. Seems like a reasonable proposal. We'll see in a second whether that's true or not.
The two furthest upfield are, my guess would be the methyls.
Maybe.
Yeah, because
Right, oftentimes they're more upfield, but look at the proton NMR. You know, it could be that they're quite different in here, too.
What is the reason to be different? Because they are same, those
well,
trees.
they're locked.
Yeah, well, I think they're just in a much different, you know,
Geometry.
yeah, so I think, remember in the C13, and I don't know if this is true or not here, you know, both of these probably have some steric constraints, right? And remember that in C13, when molecules get pushed, or atoms get pushed close together, sometimes that pushes some of the electron density back onto the carbon, and it can cause it to be more shielded. So one of these is feeling probably more steric issues, right? And I guess I would say this is probably opposite of what I was thinking when I looked at these this morning. I think these are closer together, but this one, these probably are the closest together right here. So, you know, my thought would be that,
More shielded?
yeah, that one might be more shielded.
So when looking at this, or I guess looking back at the proton NMR, with showing that.
So I think the other thing we might be able to say here is that if that one's the quaternary, these three might be the CHs.
All of them?
Yeah, because look we have this one, and this one. All are CHs. Right? So there's three, so maybe those would match to those.
What about CH trees?
The CH3s are going to be somewhere up in here.
We don't know each other?
Not yet. You know, Andrew is proposing that these could be the CH3s. And then in this whole batch, then we also have three CH2s. Right? So those upfield ones have to be the CH3s and the CH2s.
So why CHs are more downfield?
Well, I think the substitution issue, right, in all, both in proton NMR and in C13, as they become more substituted, they tend to move further downfield. Okay, so how would we tell CH3s versus CH2s?
Adapt.
Right, adapt might be a good thing to do. Oops, I don't know why they're... Okay, so we were right. Here's the CH2 for that one. Right? These three... do I have this? Are the CHs. Notice that this peak right here is mostly gone. And so this one was right. So this is a quaternary carbon. So you were right on that. What about the
CHs?
Yeah, the CH2s and CH3s?
Well, they were not. Obviously, the ones negative are...
Right, so these are the CH2s, and these two are the CH3s.
Why is it like that?
Well, I think, they're just in different, they have different steric environments and things like that.
Environment.
I guess so,
Nothing
yeah.
much different in the shapes.
Yeah. So I also did, I think that's the next one. Just for fun, I did a coupled carbon spectrum. Methyl group was the next one most downfield. I don't know if I have a setting here that makes them small every time. And so, again, we can see that the signal, for... what's happening here? For here was this CH2, right? So this is a CH2, so we see it as a triplet. Two hydrogens, N plus 1. Yeah.
And which hydrogens? Just
The two that I put the arrow to.
oh, okay.
Right, because we knew that those are the furthest downfield, they're next to the oxygen. In this next section, remember these are, I think this is the quaternary one. And this is a doublet. And I think it probably goes like this is a doublet and maybe this is a doublet.
We have more peaks right there.
Right, so there's 3 doublets because they're all those are CHs.
Oh, 3 CHs.
Yeah, and then I guess maybe somewhere in here, if this is 1 here and this one, it might be in here, and then something in here is like probably a quartet because remember But this is just a good example of why we don't usually use coupled ones, because look at how, it's not really that complicated of a molecule, but look at how complicated this section becomes, right? Because those coupling constants are big, right? And so you get lots of overlap. But, you could have situations where maybe it would be useful, right? If you wanted to, but we can... especially if you wanted to measure the coupling constant for some reason. Okay, so this is an HSQC experiment. So this is showing us one bond coupling. This stands for heteronuclear single quantum coherence. Heteronuclear single quantum coherence. Okay, so this is J1CH. All right, so, we can obviously see which protons are going to which carbons. Like we talked about before, it's a good experiment to tell where the diastereotopic CH2 groups are. There's one there. Here's one here. So these were the CHs. Here's the 2 methyl groups. Right? But what we can also do in this experiment, this one it's called a multiplicity edited HSQC. What that means is you can run it so it's like an HMQC and a depth experiment all put together. Okay, so some of these peaks are going up and some of them are going down. So if you plotted it in color, you could plot those in different colors. However, you can also tell, when the computer when you're plotting it to plot only the ones with positive or only the ones with negative. So the next one is all the positive peaks. So these are the CHs and CH3s, right? And notice we're missing all the CH2s, right? And the next one is just the CH2s. So it makes it kind of nice.
It is really nice.
And of course, just like the depth, we don't see any peaks for the quaternary carbons, right? There's no protons attached, so we wouldn't see them in this experiment anyway. All right, so here's back. We've seen this compound a few times. And so this is just some examples. We went through and drew all of the peaks and all that kind of stuff. So this is actually data from way back in, when did I go there? Like 1988 or something like that. And so some of this was kind of pretty new. So here is the C13 and the depth. The scales aren't the same. This one goes to here, and I'm having troubles here today.
What is it chemical? Is it from marine metabolite?
Yeah, it's from a marine tunicate, a sea squirt. And it wasn't a very complicated structure, but the interesting part was that most of the acidians, they tend to have these metabolites are usually nitrogenous, and this one wasn't, so that made it a little bit unusual. But so in this one, so this section right here is the same as this section right here. So scales are just off a little bit. Okay, so here's the cozy, and we can start that HA is the most downfield, so that's this one here, right? So we can follow. I have one of these or two of these, but we can follow two different splittings from this. One goes in this direction that's shown here. The other one goes, in the other direction over here. So if we start here, for example, we can go over to this one. Okay, and then from there, we could go over to here. From here, we could go, I think from that one, we go all the way over to here, into the CH2s. So that is probably the other side. So in blue, we could go to this other one, which goes into here. This goes into here. This one goes out to here. And then this would go also to the CH2s. So for this one, let's see, in blue, we started here. We went to here. So that was F, A to F. From there, we went to here, which is HC, right? And then HC went back to here, which is G. And from there, we went to the CH2s. Right, so it's pretty easy in this one to just walk your way down the spin system on both directions. All right, so here is a het core. So notice the axes are rotated. So the proton is on the this would be the F1 direction, and the C13 is on F2. Notice that this C13 doesn't look that great, so this one is actually a projection. So what it is just taking that two-dimensional data and looking at it from the side. So it's not a plot of the high-resolution C13 NMR data. Okay? And so, like we saw before, it's just telling us, which protons are attached to which carbons. And here is a long-range het core. And so this is going to show us usually J2CH and J3CH. And the challenge to this experiment is that you can't obviously tell which is which. All right, so you just have to make it so your data is as consistent as possible. So if we start with this HA, and we go across this way, we can see coupling to here, which I think is to the ester, right? We can see couplings here and here, which might be the two quaternary carbons like that, and then I think we actually even see something further down here. But, you can just piece together these quaternary positions in this way. All right, so here's just another set of examples that I just ran for fun. And this is an edited one. So we can pick out a few things here, like this most downfield one is going to be this one next to the nitrogen. And it turns out, it's a little hard to see here, but this one has a small coupling constant. And these ones next to the nitrogen tend to be kind of small, so I think the other one is over here. It's hard to see it, but there's one in there that has a smaller coupling, which would be here. And then notice there's two doublets, and this is a triplet, and probably another triplet under there, and that matches this, doublet, triplet, triplet, doublet kind of pattern around that di-substituted benzene. In here, so the next, let's see here. So these are all aromatics here. No, aromatics and double bonds. So these two, are these two, I believe. And this one, I should do a different color. This one is the proton next to the alcohol. And then you can see also a couple of, here's a CH2, and here's a CH2, and I think there might even be one up here. Okay, so let's see if that makes sense. This is a multiplicity edited one. Look at this one. So here goes to this taller peak here. That's the CH that's next to the oxygen. But also this one, notice this peak is a little bit wider. This is for the CH right here. And that's kind of has more coupling in here underneath. Okay. So those are overlapped in the proton spectrum, but they're far apart in the C13 spectrum. Right? You see that? Because we have this peak here. Okay, so this one is the one that I have in red on the double bond. And this one is the one in blue next to the oxygen. and they are just overlapping in the proton spectrum. So then we can do, oh no, it isn't. I think it was, but I didn't have the data here. Okay, so this is the HMBC, so hetero nuclear multiple bond correlation. So this is kind of the experiment that we would usually use for multiple bond one, because it's the proton detected one. So this experiment shows a few artifacts, though, that bleed through. So let's look at, say, this peak here, right? We said that that one was here. And if we look, so this one does have some multiple bond correlations here, but notice these signals right there. All right, and they don't actually match up really to anything here. So what we're seeing on a number of these in this case is that these are actually the one bond couplings, right? And they're showing up to the C13 satellite peaks. Okay, so we see one there, we see them, here, for almost all of these, we see some one bond coupling. These, I think, is a one bond coupling. So the one bond couplings show up where they are, symmetrically disposed, on each side of the signals, the proton signals.
So those satellites are produced by C13 carbons?
Yes, well, all of these are, we can only see coupling to C13 carbons, right? Because they're the only NMR active ones. But in this case, and I'm not sure quite why it does this, but I've seen this before too, where we see, this is supposed to show multiple bond coupling, but the one bond CH coupling shows up sometimes, but they're kind of to the C13 satellite peaks. And that's kind of a way that we can identify them. So it's something we have to keep an eye out for. I don't have my notes on here. So one thing in here, I think that this is actually the OH peak. And in here, we have two peaks at this position here. Maybe we should go back. So we also see that in the C13 spectrum. And notice if we look at all of these peaks that are kind of lined up with these two, some of them are kind of wide and some are narrow, right? So just by the shape of those, this wider one goes to the double bond proton because it has a lot more coupling here. And that CH next to the alcohol is much narrower. So we can pick out the narrow ones. So I think in this case, I don't have my notes, but this one is very good at actually, kind of bridging between these two structural parts, the benzene ring and then this bicyclic system over here. So we see some down here and down here. These are probably, I don't know if there's a third one. I don't like the way that this is. Oops. I guess we only see two to the aromatics, though. So if they're doing 3 bonds, then it might be going to here and here. And it's also showing some probably over to here, which is probably, say, this one. Oftentimes when we have a group like that attached to a benzene ring, though, we oftentimes see coupling to the 2-bond coupling to the point where it's directly attached, and 3 bonds to those 2 kind of ortho carbons.
It doesn't couple to the proton of the hydroxyl group?
Not usually, right?
Just to the carbon?
Yeah, the proton on the alcohols just don't show much coupling because they're exchanging. And that's why they're usually just kind of a broad. Sometimes you can see it, but if we look off of this and we look down from there, we see that there's no coupling showing up there. Let's see, the other thing we could have is this one right here. Okay, so remember what I said, that this is a small doublet and that there was a small doublet here as well. So I think we might come down to here, and this is that small doublet, and it's going to the carbon bearing the OH. So I think this one is probably going from here to here, because this carbon right here, I think, is the one that has the oxygen on it, because it's the most upfield of all the kind of the non-sp2 hybridized ones. Right, so sometimes you can see it here from kind of more the aliphatic part into the benzene ring, and we see from one of the protons on the benzene ring back the other way. Okay. But of course, it takes some time to map this all out. Okay. So the last experiment that we're going to look at here, we might look at some other kind of ones later, but is this inadequate experiment. Okay, so it shows us C13, coupling. So in this little table here, it shows the typical coupling constants. We haven't seen those before. Carbon, 1 bond coupling constants. So if they're aliphatic, it's in the 35 to 40 hertz range. Let's see, I think I have some more notes for this one. And it increases. So I guess if you have an oxygen, 40 to 60. If it's a double bond between the 2 double bond carbons, 70 to 80 hertz. If it's aromatic, 55 to 70. And if it's on a triple bond, it has a really big coupling constant between the 2 carbons of a triple bond.
I mean, they're all pretty large.
Yeah. Well, yeah, they are pretty. Yeah. Well, not necessarily for proton-carbon coupling.
No.
But for proton-proton coupling. Yes. So the way that this experiment, well, we already talked about the issues of sensitivity. But the way that this works, and I have a hard time kind of coming up. So notice the right side of this is just in hertz here. 0 in the middle, and plus and minus. And so what the book said, this axis is the sum of the offsets from the transmitter frequency. So the NMR has a transmitter frequency that's in the middle of the spectrum, usually set kind of in the middle of the spectrum. So this is the offset from the transmitter frequency from the couple so it's always just the difference from the transmitter frequency. So it's a weird axis, but down here we have parts per million. And the way that we do this is we observe coupling when we have 2 peaks that are horizontal to one another. Okay, so coupling is horizontal. so it's not like a cozy spectrum where we have a diagonal and a well, I think we kind of have a diagonal that goes between the no, we don't, because we'll see other examples. It doesn't really work that way. But so in this small molecule here, we could assign the most downfield carbon is next to the oxygen. All right, so this is going to be 1, 2, 3, 4. And we see the coupling right here from 1 to 2. So this is 1 coupling to 2. Okay. And then for 2, so 1 only has 1 peak in the vertical direction. So that means that carbon 1 is only coupled to one other carbon.
Oh.
Okay, for 2, we see that there's 2 spots vertical with carbon 2. So that means that carbon 2 is coupling in 2 different directions.
And if you have cyclic, something that has 3 bonds,
it could have 3, right. So this horizontal that we already talked about was coupling to carbon 1. This bond going horizontal is between 2 and 3. Okay, so it also goes over this way to 3, this way. And then 3, notice, has 2 peaks as well. 3 goes to 4. All right, so you can just go from 1 to 2, 2 to 3, 3 to 4. Okay, so you just walk your way down the carbon chain. Okay.
I didn't understand the offset from.
Yeah, I don't really understand that either.
Is it arbitrary, something like that?
Well, I think I tried to calculate these out before, but I didn't really. So if the transmitter is in the middle of the spectrum somewhere, then I guess in here it has to be somewhere, say down here, right? Transmitter, let's say. And it's in hertz, even though, this is like in this, so hertz are pretty big here. So this one is, I guess, is on one side of the transmitter. So it's way down by like 2,000 hertz. 2,000 hertz. The carbon 2, is on the other side, so it's like at 2,000 hertz as well. So, in fact, our transmitter, I guess, would have to be like almost evenly between these two, right? Because this is 2,000, this is 2,000 in the other direction, right? And then 2 and 3 to 4, this coupling. Yeah, I'm not sure.
The other one is?
Because we only really have 3 cross peaks, right? Sets of cross peaks. They're not really lined up with the chemical shifts of something. So what did I say? It was the sum of the offsets. So, of 1 and 2, and of 2 and 3, and 3 and 4, I guess. Right? So, let's try this again then. Not there. So let's say the offset was somewhere in the middle then again. And maybe this was at 2,200, and this was at 200 in the other direction, right? And we sum those, and they have an opposite sign, let's say this one's, I don't know, these don't seem to have negatives and positives, but if this was negative 2200 and this was positive 200, we'd sum those and we get a negative 200, right? And then coupling between 2 and 3, this is like at 2000 as well, so this would be like 1800 here, and so 1800 and 200 would be about 2000, right? And then if this was 1800 and this is, yeah, even more, that's over 4000. So this would, I don't know, would be like 2300 or something like that. And that would be over 4000. Right, so we have the transmitter in the middle, which is just set at 0. And then I guess it's the sum of how far they are away. I don't know quite why they do it like that. It seems like, it'd be nice to just have it plotted out like a cozy or something.
Well, is it informative or just?
Huh?
I think, is it informative or not?
What?
The offset that they put over there, it doesn't matter.
I don't think it really matters to
matter at
us,
all.
but it's just, it's kind of troubling if you don't understand what what the
Scale.
axis means.
We could just ignore it.
Yeah, we can ignore it, yeah.
That's what I've always done until right now.
Well, because on the diagonal, if you have that diagonal and you already have a really low sensitivity experiment, if there are carbons that are coupled together that are very similar shifts,
Right.
you won't see it past
Right.
the diagonal. But with this, possibly you could see it, but because
Maybe. But if they're right next to each other,
you still have that.
yeah, they'd still be like... So I think that this does kind of have a diagonal here where the offset is or something. Because look at the next one. And then, gosh. Okay, so this is another terpene. It's called caryophyllene oxide. And, obviously it's a lot more complicated. Oh, this one, I think, had a problem with it, though. Something was wrong. Okay, so a few things that we could maybe pick out here would be, because I think when you're if we're just assigning, then just like in any of these, it's best if you can pick out something, right? And so the easiest thing to pick out is the carbons on the double bond, right? So these two carbons here, so we've got 8, these are already labeled, 8, and 13 is the terminal one.
So why they're easier to pick out?
Well, because those are the only double bond carbons in the spectrum, right? So they kind of stand out from everything else.
55 to 70?
Hmm?
From 55 to 70 or?
No, the quaternary one is at like 150, and the terminal one is about...
Based on this table.
Oh, the coupling constant? Well, I guess this experiment is run to observe all those sizes of coupling constants for some reason. It seems like oftentimes in the pull sequences there is some delay that's related to the coupling constant. Remember, we had these delays of 1/2J or something like that.
So we cannot use a table, just looking at this.
Those were just examples.
Okay.
Maybe you can optimize the experiment based upon what kind of molecule you have, because if you're have a lot of aromatics, then maybe you can set it so it's better to match the coupling constant between aromatic carbons or something like that. When I was a postdoc down at the University of Utah, we were working on these compounds from marine sea squirts, and they have a lot of kind of polycyclic heteronuclear ones. So aromatic with lots of rings and some nitrogen stuck in there and stuff. And they're tricky to solve because, usually you'd use like an HMBC to put things together, but there's sometimes fewer protons around the outside, and then you have these carbons that are like buried in the middle of this aromatic structure. And it's hard to see coupling from some of the protons on the outside to the carbons in the middle. So it wasn't my project, but one of the other postdocs had this one, and they decided that they were going to do a inadequate on it. And they had to run that spectrum for like at least 1 week. I don't know if it was even longer than that. So it was really long because it was so insensitive. And I think the NMR guy was down at University of Utah, had this program. They ran it such that I think the peaks that were coupled would be offset in phase. And he had this program that could search through the data to try to pick out these offset peaks, even though they were like just almost in the noise. But in fact, they still didn't, even after a week or something, it still didn't really, they couldn't see what they wanted to. Oh, and the other thing that they did was, the other issue is because remember that the C13 T1 values are much longer too. And especially quaternary carbons inside of a ring, they could be like, 10 seconds, or maybe they were even longer. And so that means you'd have to wait a long time between pulses too. So what they did is they added a small amount of a paramagnetic species to cause the relaxation to be much faster without being too fast, right? All right, so we could start there. Of course, the terminal one, C13, only couples to one carbon, right? So it couples down here to C8, and notice the 8 couples to 2 other carbons. So one of them would be going to 9. So let's say that one of them is going to 9. Right, and so that would likely be, I think, because it's tertiary, probably further downfield than 7. So it would likely be here, would be 8 to 9. And then the other one over here might be to 7. Oops, I should have made that a different color. Okay, so the next spectrum, 40. See, nothing is going at 40. So in the book, they make that one to 9. Is a blow up of this region. But when I was working this out, I noticed that, let's see, that this isn't quite right. That, let me just get this right. 50. I think that this one is not right. Because let's look back at, I've had this a little bit wrong. And so this one, in fact, should be going, what color did in blue, should be right 50, just under here. Okay, so this is actually 9 up here, and the challenging part is that this other one coming in at 30, there's actually 3 peaks up in here, but one of them was 7. There's one of them up in here. Okay, so let's see if we can do this. So from 9, let's go from 9. 9 goes, notice it has 2 other, well, let's see, it should have, yeah, 1 goes back to 8. That's the one that we are off screen now. 1 goes right here. And so this goes to compound number 1. Okay, so that's going from 9 to 1. Okay, the other one that we can see is right here. And so that is going from 9 to 10. All right, because it's getting split from this. 1 goes to 10, 1 goes to 1. Right, so this is going to 10. All right, and so let's go from 10. So there's 10. 10 goes right here. Should go to 11. Right, so that's 10 to 11. 11 has a, look at that. It has 1, 2, 3, 4 couplings, right? Because it has those 2 methyl groups on there as well. Okay, so we want to go back to 1, though. So 1 right here. So this one goes from 11 to 1. Right? You see that? And then I'll just do them in black. The other ones must go to the methyls. So one of these has to be a methyl. So we have 14. It's got to be one of the ones in here too, I think, the way I had it. And the other one is like, I don't know which one is which, but like 15.
Wouldn't 15 be the more... Yeah, no, 15 would be the more down upfield one.
Well, they're going to be like this, so
but
I'm
you
not
also
quite...
have that proton sticking up from 1.
Yeah. But I think it depends on how this whole thing is like bent and everything. Next, where they are relative to the double bond and relative to the epoxide and such. So I don't know if I did that assignment or if that was in the text already. Okay, so we made it to 1. We made it around that ring. So let's go back and look. I wonder if I can have more colors here. That's not very many colors. Dang. I think I used a different program last time because I had it all nice with all kinds of colors in here. Oh, well, I'll just use it. So from 1, if we look along 1, we've accounted for this coupling and this one. This one we haven't done yet, right? So this is going to be 1 to 2. 1 to 2. Okay, and then 2 has another coupling. 2 to 3. All right. 3 right here. 3, if we go down to here, we got that one. It's going to come down here. So this has got to be 4. So these 2 are on the epoxide, I think. Okay, what color should I do that? 3, where was I? 3 Oops, that's not what I wanted. Three, it goes to 4. And go back to here. 4 goes to here. Let's say 4 going to, 3 to 4. That was blue. 3 to 4. 4 to 5. Right? And also, use this one black. Right? It's kind of blocked here, but 4 also has another one. So 4 is also going all the way over here. So this is going to be 12, the methyl group. All right, so we're at 5, and 5 here. 5 goes to, and here as well, 6. So we have 6, 7, and 14 all in there. And so, yeah, they have a little one that shows here. So I think this is the place, just like we were talking, like 6, 7, and 14 all together. 6 and 7 are next to each other, right? So they've identified, I left this here, just right here, those are those two coupling right next to each other, right on this kind of diagonal. So I could do this. This would be in blue. 6 to 7 is going to here. And then 7, one of those has to, maybe I have it blocked. That's it right here. There. From 7, we're going to go down to here, and this was 7 goes to 8. Right, that came out to the other part. So in fact, with this spectrum, we can just, because this is one entire spin system, we could just walk our way all the way around this. So it is a pretty amazing experiment.
Yeah, but you will never do it.
Well, if you have a lot of sample.
Yeah, or you have an enriched sample.
Yes, or less, yeah. So they can use some of these kind of things too, like if they're doing biosynthesis, right? So sometimes they can feed a microorganism like C13 labeled acetate, right? And that gets incorporated into the molecule, and so you only see in those cases, is there sometimes these polyacetates can be like double bonds like this or something. And I think the actual acetates are between here and here and here and here. And you run the experiment and you only see these two coupling and these two coupling. And it just tells you where the acetates were incorporated into the structure because you have these little pieces that show up very well in the experiment like this.
Well, yeah, and then you could also, you'd have to run it side by side with the carbon 13.
Right.
Unenriched carbon 13.
Mm-hmm. Right.
Huh. That's cool. That's cool.
So we're about out of time. I think that's my last one for today anyway. Okay, so next time, we're just going to work our way through some problems. Yeah, that'll take us probably all of next time. All right?